Inside a modern jet engine, it is incredibly hot. In fact, it runs about 250 degrees Celsius hotter than the absolute melting point of the materials it's made from. Despite this meltdown scenario, there are over 10,000 passenger planes in the sky right now, perfectly safe, relying entirely on this seemingly impossible physics. This chart shows Carnot efficiency, the direct relationship between internal combustion temperature and engine efficiency. To get enough thrust for a commercial airliner without wasting fuel, the core has to reach an inferno of around 1,500 degrees Celsius. And heat is only half the battle. Inside that core, hundreds of glowing hot turbine blades are spinning at 12,500 revolutions per minute. At that speed, the centrifugal force trying to rip a single 300-gram blade apart is equal to the weight of 20 metric tons. Engineers are caught in a brutal trap. We demand extreme heat to make commercial flight viable, but that exact heat causes traditional metals like steel and titanium to stretch, permanently deform, and eventually snap under the immense load. To push past the limits of standard metals, metallurgists created nickel superalloys. By carefully mixing in specific elements like aluminum, they redesigned the metal itself at the microscopic level. When you zoom in, the microstructure looks like a chaotic city grid. You have regions where the atoms are randomly placed, forming these rod-like shapes, intersecting perfectly with repeating, ordered cubes of atoms called blocks. When a metal gets hot and experiences extreme stress, microscopic flaws called dislocations start moving through the atomic structure. As these flaws slide freely through the chaotic rod sections, the metal physically stretches in a process called creep. In these nickel alloys, the heat actually triggers a defense mechanism. As the temperature rises, the extra thermal energy causes these dislocations to jump to a different atomic plane, a process called cross-slip. Once the dislocations are separated like this, they can no longer travel together through the lattice, locking them permanently into place. Because of this specific atomic maneuvering, the superalloy doesn't soften as it gets hot. Instead, its strength actually peaks right at the extreme temperatures, where other metals would simply give way. But there is another structural flaw to deal with. Even superalloys are normally made up of millions of individual microscopic crystals. Under extreme heat, the jagged borders between these crystals act as superhighways for atoms to slide past each other, leading to structural failure. To solve this, engineers set a goal that sounds absurd. They decided to cast the entire 300-gram turbine blade out of one single unbroken crystal, eliminating internal borders entirely. They start with a wax mold, which is filled with molten superalloy inside a furnace. The mold is then slowly pulled out of the heat from the bottom up, encouraging tall columns of crystals to grow vertically from a cooled base. Selection happens at the base of the mold, where a helical passage known as a pigtail is added. As the crystal columns grow into this spiral, they crash into the upper surfaces. This physical bottleneck chokes out every competing grain until only one single crystal makes it through to fill the rest of the blade. Forcing billions of atoms to perfectly align into a single continuous crystal lattice removed all the internal weak points. This multiplied the lifespan of the blades and made the grueling flight schedules of modern aviation possible. Yet, even with a flawless single crystal superalloy, there is one unavoidable reality. If you put it directly into a 1,500-degree gas stream, it will physically melt. The blade survives because it isn't a solid chunk of metal. It's hollow. Inside is a complex, ribbed, maze-like network of internal cooling passages. Air from the compressor is pushed through this hollow core. It bleeds out of tiny microscopic holes on the surface in a process called film cooling, forming a continuous protective boundary layer over the metal. As a final layer of defense, the outside is sprayed with a 1/4 millimeter thick ceramic coating. This acts as thermal armor, insulating the metal beneath it by up to 170 degrees. This creates a thin, protective envelope of air and ceramic that keeps the metal significantly cooler than the surrounding gas. By sweating cooler air and wearing ceramic armor, the blade survives while submerged in an inferno. Operating on this extreme edge comes with modern risks. Today, the relentless enemy of a jet engine is microscopic atmospheric dust and sand ingested at cruising altitude. When this fine dust hits the hot section, it melts into a thick, glassy sludge. This sludge oozes over the blade, plugging the tiny film cooling holes and ripping away the ceramic armor, eventually causing the engine to burn up. We push our engines this hard because the alternative is highly inefficient. Early jet engines from the 1940s ran at much lower temperatures and could barely fly for 10 hours before their internal components began to fail. Mastering this single piece of metal allowed planes to fly further, carry vastly more weight, and burn far less fuel. It took commercial flight from a rare, expensive luxury to an accessible global standard. The entire massive infrastructure of global transit, safely carrying millions of people across oceans every single day, rests on our stubborn refusal to accept the physical limits of a piece of metal.